let's get started today. We got 3 items on the agenda today. We want to finish up lists, and I'll do that by going over the diamond hunter example in Dr. Plank's notes. Then we're going to briefly talk about BigO. We'll actually discuss BigO in more detail at the end of the semester, but when we compare data structures, we want to be able to compare their running times, their efficiency. And BigO notation gives us a way to compare the efficiency of 2 different data structures, or actually 2 different algorithms. And then we're going to get into sets and maps, which will actually be the last 2 data structures you'll be introduced to this semester. Did want to point out there's no class on Thursday because of Engineering Day. The Engineering College cancels all engineering classes on that day. It does not cancel your Gen Ed classes or any other classes across campus, so you're still responsible for attending any non-College of Engineering class. And of course, if one of your professors goes against the engineering college, then obviously you have to go to that class too, but they've been pretty firm about the fact that we should cancel. So there is, however, the problem with the engineering college doing it is that the fall semester is already shorter than the spring semester, and I can't really afford to lose the lecture day. So fortunately, the lecture normally scheduled for Thursday is not quite so important as other lectures. It's a reinforcing lecture on sets and maps. So I have a video lecture for it, and you will be assigned the task of reading up on that, or not reading up, but watching that video lecture on Thursday. So if you look at October 20th, you see no class because of Engineering Day, but read these notes, and also this is the lecture that I want you to watch, and start at the 8-minute and 30-second part, because the earlier part is just housekeeping from an earlier semester. Okay, so you are responsible for the material that appears in those notes, and you can be tested on them, so make sure that you do watch the video. Okay. Also, you can put, YouTube allows you to set the audio to speed it up, and I found that I sound good at 1.5 times normal speed. So, in fact, studies show that people actually seem to understand and learn better at slightly accelerated audio speeds. Normally, the pace at which we talk is a little bit on the slow side, believe it or not. Okay, so wanted to start by finishing up with lists and iterators and the like, and it's a final example that Dr. Plank has, which he calls the diamond hunt example, because it's taken from Topcoder. And the idea is that you have a string of less than and greater than signs that occasionally form a diamond. And what you want to do is count the number of diamonds in this string. But it's not as simple as simply counting the number of diamonds you see. So for example, here you see 2 diamonds, yet it says there's 3. Here you see only 1 diamond, yet it says there are 9. So there's an extra wrinkle to this problem. And the wrinkle is that when you find a diamond, you delete the diamond from the string. And if the deletion creates a new diamond, then that new diamond also counts. So for example, with this string right here, we start by finding that diamond. Okay, so when we delete it, we'll now have something that looks like this. Okay, so that's this string right here is this string with this deleted. Okay, then we can find this diamond right here. Okay, now once we do that, let's make it more obvious by erasing. Do you see that a third diamond has appeared? Right? There's a third diamond, whoops, right here. So that becomes diamond number 3. So then we erase it. And now you can see there's no diamonds left in this string. So that's how we come to 3 there. And it should be clear that when we start deleting a diamond here, that immediately creates a new diamond here, so on and so forth. Well, it turns out that you can solve this problem efficiently using a list. So what we can do is basically read in the string and create a list of characters where each element of the list is one of these characters. Okay? So he actually has a brute force approach using substrings where you simply search for a diamond string, because that's an obvious brute force solution. Okay, you can do so his obvious brute force solution is to search for a diamond, and if you don't find a diamond, you return the number of diamonds seen thus far. ND represents the number of diamonds. If you do find it, you increment the number of diamonds, and then you create a new string by deleting the diamond you found. So you take whatever is before the diamond and you concatenate to it whatever is after the diamond. Now that works, and it's a straightforward solution, but it's very inefficient. And we keep stressing efficiency in the course. And the reason it's inefficient is that this concatenation process is inefficient, because if the string is originally n characters long, then the concatenation requires a string of how many characters? How many characters must be concatenated together if the original string is n characters and you're removing a diamond? N minus 2. Okay, so in the worst case, there's going to be close to n diamonds in the string. And if you multiply that by n minus 2 characters, you come up with n squared minus 2n characters that you're concatenating, plus this find operation in this worst case where in the worst case, what you're really looking at is this string right here. Okay, this is kind of your worst case string. So in that string, the find is always coming in at is having to look at n divided by 2 characters before it finds the diamond. And again, there's roughly n diamonds, so the find is also looking at roughly n squared divided by 2 characters. So your running time is going to be proportional to the number of characters, and if your string is big, n squared is going to grow very quickly, as hopefully you saw in that one chart you saw in Zyanti. Zyanti had a chart showing how different running time functions blow up, and n squared is a very fast growing function. So we would like to see if there's a faster way to do it. Maybe that's proportional, is linear in the size of n rather than n squared. And doing it with a list will achieve that purpose. So what we're going to do, as I said, is we're going to create a list. and each element of the list is going to have one character from the string. So the list will have n elements. And what we're going to do is we're going to have 3 iterators. So we're going to have a left iterator, which is always supposed to point to a left or a less than sign. The right will always point to the next element immediately to the right of left. Okay? So what's going to happen is we're going to always move left until we find a less than, because a diamond starts with a less than. When we reach a less than symbol, we're then going to look at right, or we're actually going to increment left by 1 to give us right, and we're going to see whether right points to what? What do we want right to point to if we have a diamond? A greater than. So obviously here, that's not pointing to a greater than. So in this situation, we would move on because right isn't pointing to the right thing. So we would move left over, and now left would point here. And again, because left points to a less than, we'll now take a look at what right is, and this time right is the right thing. It's a greater than. So we would increment the number of diamonds. Okay, so it started at 0. We'll set it to 1. And now we need to delete these 2 from the list. And remember, that's an efficient operation in a list. Deleting from the middle of a list is very efficient as long as we have pointers to the elements we want to delete. It's a constant time operation. Now, once we've deleted these 2 elements, we need to reestablish left. So that's where the 3rd iterator comes in. And the 3rd iterator, where does he have it? Up here. Yes. He calls it new left. So in this case, what do you think new left should be? Once we've deleted these 2 items, what should new left, or what should left become? Should it become this one or this one? Okay, I'll take a vote. Okay, how many think it should become, the new left should be this one? Raise your hands. Okay, and how many think it should be this one? Very good, it should be this one, because when we delete it, we now want to see whether we have a new diamond, and we have to do that by moving back. Okay, so the 3rd iterator is always telling us where the new left will be. And the reason we have new left is what happens when we delete left. Well, it is handed back to the memory allocator, and it's allowed to completely erase the contents of left. And one thing it turns out that lists have is not only do they know what their successor is, they also know what their predecessor is. That's why reverse iterators work. These lists are what we call doubly linked lists. They have 2 pointers, one to their predecessor and one to their successor and one to their predecessor. So before we delete left, we need to save its predecessor, which is going to become the new left. If we don't do that and we delete left, we have no guarantee that we can ever get the previous element because the memory allocator is allowed to wipe out the contents of left. So before we delete left, we need to save its predecessor. So that's why we have new left. Okay, and there's one more case that we have to consider okay, in that case, is the case where we immediately have a, so let's say this is left and this is right. And now if we delete left and right, well, the first element is now the sentinel node, and that's no good because we can't examine, there's no value in the sentinel node. So there's a special case where left is the first element in the list, in which case we want to resume with what is the new first element in the list. So there's a special what we call boundary case. Remember from 102, boundary cases are these unusual things at the beginning or end of your data set. So in the special case where left is the first element in the list, we actually need to start with the new first element. Okay? So does the algorithm make sense? In fact, Dr. Planck does a quick example with it. So initially we have this situation, and then we increment left and right, and you can see that now they point to a diamond. So he increments diamond to 1, sets new left to be left's predecessor, and then he deletes left and right, creating this new list right here. Okay, now left and right form a diamond, so he increments diamond to 2. And now we have the special case where left is the beginning of the list, so we set new left to be what will be the new first item, and the new first item will obviously be the item right after right. Okay, so again we delete these two and end up with this list. Okay, now even though left points to a left inequality, right doesn't, so we advance left, and now left and right do point to a diamond. We again make new left point to the predecessor, delete these two. As you can see, there's only one item left in the list. Right now points to the sentinel node, so we're done. Now at each point, the deletion only requires a constant time operation, and at worst, we simply back up the pointer by 1, but in backing it up, we've actually deleted 2 items from the list. So we may back up the pointer by 1, but we've shortened the list by 2. So in fact, we've kind of moved forward, in effect, 1 element. And it turns out that this particular algorithm is linear in the number of characters in the strings, whereas the previous one was n squared. So this one is much faster. Okay, and the algorithm, or the code, looks as follows. So it is a lot more complicated. Turns out this one, the inefficient one, was very simple. In this case, in fact, it is relatively complicated. So we start and we iterate through our string, and we simply push back the characters onto our list. So our list is a list of chars. We simply push back the characters of the string onto this list. Initialize the number of diamonds to 0 and set left to be the first element of the list. And now while left is not equal to L.end, okay, if the left character is a right inequality sign, that's no good. That's not the start of a diamond, so we increment left. Otherwise, what's the else? If we get to the else part, what do we know about left through deduction? What is it? It must be a less than. So we set right equal to left, and then we increment right. We can't say right equals left plus 1. Might be nice, but we can't. It's not set up that way. So we make right point to the left element and then increment right. If right is at the end of the list, obviously it's not a diamond, so we immediately return ND. We're done. Otherwise, if right is a left angle, it's obviously not a diamond, and therefore we increment left. Okay, it now points at right. Else, right must be a right angle, and thus we have a diamond, so we increment ND++. And in that case, we need to figure out what new left is first. So we check to see the special case. If left is the beginning of the list, new left becomes right plus 1. Otherwise, new left becomes left minus 1. We move to the left of left. And then no matter what, we erase left and right and set left to be new left. So it's exactly what we said. It just takes a bit of time to write that code. Okay? But it all works. And he actually does run this version to show you how fast. So he starts with a list of bad diamonds. Remember, the bad diamond is this one. It's the one that makes the previous algorithm really bad. So it makes a bad diamond with 1,000 characters and runs it. It's 0.02 seconds with our new algorithm. With 1,000,000 elements, it's 0.47, so it's about half a second with our new algorithm. Okay? He also ran it with the previous algorithm. Notice, first of all, he didn't even bother with 1,000,000. At 100,000, it was already at 79 seconds. At 1,000,000, it would be about 100 times, the string would be 10 times bigger. And since it's proportional to n squared, it would run up roughly 100 times slower. So it would be roughly 7,935 seconds. Okay, there's 3,600 seconds in an hour, so it would have taken roughly 2 hours to run on a 1,000,000-character string, whereas the second algorithm took half a second on a 1,000,000-character string. That's a huge difference, and that's why we care about efficiency. Okay, the difference between half a second and 2 hours on a string that's 1,000,000 characters. That's the difference between n and n squared. Okay, so that actually does give us any questions about this. We good? Okay, so that allows us to segue into BigO notation. So the book does it in the middle of its searching. And the basic idea when we are comparing the efficiency of two algorithms is we want to come up with a rough estimate of the number of instructions that they execute. And for convenience, we tend to say that one instruction takes a unit of time. Now, it's true that integer add is faster than floating point add, or that a print statement is slower than a floating point multiplication. But we tend to assign unit time to most of our instructions. Now, not a function. A function, you have to count up all the instructions that function is executing. But things like plus, minus, string, it depends about string concatenation. If you're creating a totally new string, that's a order n operation. But so you have to kind of be careful about what you're counting as unit time, but the basic idea is we're counting the number of instructions. And we want to express the number of instructions executed as a function of n, where n is the size of the input. And I believe on the last day of the semester, we'll talk about how you read code and you count instructions. We won't do that today. Today, we'll assume that we have come up with the equation that gives the number of instructions executed. And we'll call that the running time. So this says algorithm steps, but it's essentially the number of instructions executed. And we will call this running time. So clearly, one algorithm is preferred to another. If we have two algorithms, and this is n on the x-axis, and this is f of n, which is our running time, clearly algorithm 1 should be better than algorithm 2 if at some point there is a x such that for all n greater than x, that algorithm 1, there's running time, is less than the running time of algorithm 2. Okay, so what we're looking for when we consider efficiency is that as n grows large, does one algorithm consistently run more quickly than the other algorithm? For small n, we really don't care, because for small n, almost all algorithms will run very quickly. But for large n, like n equal 1,000,000, that changes. Okay? So when we consider large n, it turns out that only one term in our function matters. And what term is that going to be for large n? The highest power. The term with the biggest power is the only term that will matter as n gets big, because it will dominate every other term. So when we consider BigO notation, what we want is a succinct shorthand for how fast an algorithm runs. We don't want to have to give the full equation. So since the largest term dominates every other term, we simply choose the largest term, which in this case is n squared, 7n squared. Now, we further simplify because the constant doesn't really matter in this case. Okay, if we're comparing 100n, if we're comparing 5n, nope, I did have it right. If we're comparing 100n and n squared, it's true that the coefficient on 100n is a lot greater than on n squared, but at what point does n squared permanently become greater than 100n? For 100. So for x greater than 100, n squared is always greater than 100n. So the constants get swamped as n gets large. The constants no longer make a difference. So we also eliminate the constants from our term and end up with just the factor, which in this case is n squared. So what BigO notation does, it's essentially shorthand. It finds the biggest term in the running time, or then the function that determines the running time of an algorithm. Then it eliminates the constant factors from that term, and that gives us the BigO for that particular function. If you wonder why big O, I can't tell you other than that. It comes from math. Someone who's a math major might be able to tell me why mathematicians use big O. But no, I will not be saved by a mathematician. At any rate, they use big O for this purpose. So in this case, we would say the running time of this particular algorithm is O(n) squared. We don't say big O. The reason it's called big O is it's a capital O. But we just say O of n squared. Okay, so there's a couple, let's see. So there are a couple rules. Again, if you multiply it by a constant, we don't care. If you add a constant, that doesn't matter because a constant is swamped by a larger order term. However, multiplication is different. If we have n times O of n squared, that is actually O of n cubed. So for example, let's say that a loop requires, let's say the loop body for blah, blah, blah. Let's say the loop takes n squared time. And let's say the loop runs n times. Then we say the loop body is order n squared. And since the loop runs n times, it makes sense that the total running time of the loop is n cubed. Because each iteration executes n squared instructions, and we execute those n squared instructions n times, hence n cubed. So when we multiply order f of x by g of x, then we get O of g of x times f of x. And also, if we do addition by 2, then it becomes g of x plus f of x. Now, if it's something like n plus n squared, we obviously want to take the bigger of the two. So a better way of saying this would probably be big O max of g of x and f of x is what this really should be, in my opinion. Okay? Although what they're catering to is the rare situation where there's two different inputs. Okay? In Lab 7, there's two different inputs. In Lab 7, you're dealing with Coke codes. There's Dr. Planck likes, if you open a bottle of Coke, on the cap, there's a code that you can actually enter for prizes. And in that lab, there's actually a number of inputs. There's the Coke codes, there's the prizes, and there's the users. There's actually 3 inputs. So it's as though there's C Coke codes and U users and P prizes. So there's 3 inputs. So in that case, you actually have functions that are in terms of, you have f of c plus g of u plus h of p, and in that case, you may not be able to figure out which is the max, because in advance, you don't know how many Coke codes there are, how many users, and how many prizes. So in this case, you would actually write the big O running time as that. You would say it's big O of f of c plus g of u plus h of p, because depending on the sizes of c, u, and p, one of those 3 terms could dominate. But as you vary the sizes, which term dominates changes. So you can't be sure in advance which of the 3 terms dominates, and therefore you write big O as the sum of the 3 functions in that case. But if you have a direct comparison like it's order n plus n squared, that's clear. It's order n squared because n squared is the bigger term. So questions about that? Yes?
Actually, I just did a quick Google. Big O stands for order.
Order. Yep, okay. In fact, you heard me a couple of times saying order of n squared rather than big O. So I guess I knew it without, thank you. So O stands for order. And the one thing I did not have you do, so it showed you some examples of running times, assuming that each instruction takes 1 millisecond, which is actually fairly conservative. These days it would be more like, 1 microsecond. These days it would be more like 1/1,000,000th of a second. But nonetheless, it gets the point across. So these are the most common functions. Okay, log n is sublinear. And it is what we get with binary search. Okay, so with n equals 10, it's 3.3 microseconds. At 100,000, it's still very small, 16.6 microseconds. N linear in the size of the input. That's linear search. Okay, it's 10 microseconds at n equal 10, but at 100,000, it's up to 1 second. Notice how the log just beats it hands down. So log really grows much more slowly than n. This n log n comes up often. It's called log linear. And most of the sorting algorithms are log linear that we care about. Merge sort and quick sort, which you'll learn about in CS302, are fast sorting algorithms. They are log linear. And you can see that with n equals 100,000, it's 1.67 seconds. So log linear is not horribly worse than n, right? In fact, it's looking like it's looking in this case to be less than 2n. It's not bad at all. Okay, n squared is the thing though that starts to blow us away. N squared, which was what our diamond hunt naive algorithm was, 2.7 hours at 100,000. Remember when we did the 1,000,000 character string, it went from half a second to 2 hours. So n squared blows up very fast. N squared is much, much worse than log linear. So log linear we're happy with, n squared not so much, although many of the algorithms we use in practice are n squared. Okay, then n cubed, not so good, but the obvious version of matrix multiplication is n cubed, because a matrix is n squared elements, and doing the obvious straightforward matrix multiplication gives you n cubed result. You can see that for 100,000 we're up to 31 years. That's horrible. But the worst is what are called exponential algorithms. These are algorithms that are 2 to the n power, some exponent to the n. So computing Fibonacci numbers in the stupid way is c to the n. We'll go over Fibonacci numbers when we get to recursion, but there's a clever way to do Fibonacci numbers and a not so clever way. For those of you who don't know what Fibonacci numbers are, f of 0 is 0, f of 1 is 1 for Fibonacci. F of the nth Fibonacci number is f of n minus 1 plus f of n minus 2. Okay, and the dumb way to do it is, well, f of n minus 1 is f of n minus 2 plus f of n minus 3 plus f of n minus 2. Okay, and you keep doing this, and it turns out you calculate the same term multiple times, and it gets to be exponential. Another example is the traveling salesman problem. You have a traveling salesman who has to go to some number of cities. You want the traveling salesman to go to each city once, and you want to minimize something like the number of miles that the traveling salesman travels. Well, it turns out the only real way to minimize the circuit is to look at 2 to the n is all possible arrangements of cities, okay, which is actually n factorial. And n factorial is greater than 2 to the n. And there are some problems in computer science that are conjectured to have as their most efficient solution an exponential algorithm, that's the best you can do. The traveling salesman problem is one such problem. Mathematicians and computer scientists have spent years trying to find an efficient polynomial solution to the traveling salesman problem and have not succeeded. It's now conjectured that the best you can do is some fraction of n factorial. Okay, and this just grows super fast. You can see here that at n equals 50, you're already at 35.7 years. It really doesn't matter how fast we make computers. Computers will never catch up with 2 to the n. Okay, because each addition doubles the running time of your algorithm. Okay, there's the classic or the good fable of the king who is so overjoyed at some invention that one of his subjects comes up with that he offers as any reward. And the subject says, "Oh, very humble man, here's a chessboard with 64 squares. All I ask is that you start with 1 grain on the first square, and each time you double it. So 2 grains on the second square, 4 grains of wheat on the third square, 8 grains. And the king, thinking, wow, this is a very humble subject, agrees and immediately is bankrupt. Because 2 to the 64 is actually more than the number of atoms, I believe. It may not be more than the number of atoms in the universe, but it's, I think, on the order of that. So in fact, there weren't enough atoms in the universe to fulfill that particular order by the time it got to the 64 square. So essentially, you can look it up. It may not, I may be slightly low on that, but I'm not far off. At any rate, if you have an algorithm that's 2 to the n, you're not solving it for anything other than n probably less than about 10. It's that bad. Okay, and they actually gave you a nice little graphing tool. So the absolute best algorithm is order 1, constant. So if something is constant time, we just say order 1. We don't say order 5 or BigO 10 or BigO 50. We say BigO 1 to indicate it's constant time. Okay, and access into an array is constant time. Removing something from the end of an array or a vector is constant time. For a list, inserting into the middle of the list if we know the target element we're inserting before or after is constant time. Did you find it?
It's the number of atoms in our solar neighborhood.
Okay. Is 2 to the 64?
Yep.
Okay. Thank you. So obviously, if that's the number of atoms in our nearby solar system, there's not enough atoms or grains on Earth to satisfy that humble subject's request. Okay. So, order 1 is best. You can see log n here goes up very slowly. Okay? Order n goes up much more quickly, but it's still not bad. At 10 number of elements, the number of computations is still n. Log linear, still not bad. We're only now at 22 at 10. But order n squared is all the way up to 100 now. It's 5 times greater. 2 to the n, horrible. At 10, it's already up to 1,000. And order n factorial, which is the traveling salesman, at 10, we're already up to, is it 3 million? Yeah, about 3.5 million. Okay, so n factorial even worse than 2 to the n. But you can see from this little thing how the different functions are. Basically, we strive for something that is log linear or better. Okay, log linear or better is our best shot. Once we get to n squared, our algorithms slow down considerably. Okay, so questions about BigO notation. We will be using BigO notation to compare our algorithms. For example, we said that for the most part with hash tables, now we can talk about average case and worst case. So with hash tables, the average case is constant time for a find. For an insert is constant time. And for a delete is constant time. What is the worst case, though? What if they all hash to the same bucket? What does it reduce to? Okay, think about separate chaining where everything is put in a list. O of n. Now, we would say O of n for find because we want to make sure it's not already in the list. If all we have to do is add, it would still be O of 1 for insert. But we generally say in the worst case it's O of n. But as long as we choose good hash functions that randomize well, it's going to be order 1 for hash tables. Today, we consider two new structures called maps and sets. Okay, they do the same thing. They store a collection of items and keys, and we want to be able to look them up efficiently. We want to be able to find, insert, and delete them. So, turns out that each of these requires log n time. And also in the worst case, we can guarantee log n time. Now, you might wonder if this is a set of operations, which looks to always be better? There's a clear winner here if these are just the three operations. Come on. We just went over BigO. Don't be bashful. Why sets and maps?
Less than linear.
Okay, but constant is even better. So actually hash tables are the clear winner because linear, here's linear. Linear still beats log. Okay, constant is absolutely the best.
I'm still not looking up yet.
Don't worry, I'm not a morning person either. So we generally prefer hash tables. Okay, even though the worst case is worse than the worst case for sets and maps. So one reason we might choose a set and map is if we absolutely have to have a guarantee that the worst case will be no worse than log n. But realistically, the hash tables that are used in practice use good randomization algorithms, and they don't run in the worst case time. They run in the average case time. However, there is sometimes the requirement that we keep the data ordered or sorted as we do our insertions. Okay, one reason is that we may periodically want to print our data and we want to print it in sorted order. Okay, perhaps we want to periodically print it in sorted order. Okay, and another thing is perhaps we perform what are called range queries. So a range query is one where we ask for all values between x and y. Okay, so a range query says give us all keys in the range x to y. Whereas a point query just says give us the key. A point query just says give us the key where key equals x. So a point, we only want one point. Whereas a range query, we want everything in the range. So I might say, give me all employees who earn between $10,000 and $50,000. Or I used to be a runner, give me all runners who finished the race in less than 15 minutes. Those are range queries. And they require, for an efficient solution, that the values be kept in sorted order. Okay? With a hash table, if I say, give me all runners who finished in a time of less than 15 minutes, the only way I can solve that problem is to search the entire hash table and look at each key. And that's inefficient. That's an order n operation. But if I've kept the data sorted, now I can, once I find the key that is equal to x, I can simply move forward linearly because the values are contiguous until I reach y. So I can perform, in effect, a point query on x, which takes log n time, and from there on, it's constant time to find the next element. So sets and maps are good if we either periodically print the data in sorted order or if we are performing range queries. If we don't have to perform either of these two operations, we should prefer hash tables. Okay, now Dr. Planck, I think, devalues hash tables. He prefers sets and maps. But you should know that actually in practice, it's much more common to use hash tables. Okay, and scripting languages use hash tables for this reason. However, today is devoted to sets and maps. The nice thing about sets and maps is that their interface is essentially similar to lists. Let me give you a quick overview of what sets and maps do. We'll get into the details later. But essentially, what they do is they store things using what's called a tree-like structure. So let's say we have the value 100. We might say that is the so-called, don't take notes on this yet, we'll get to it. This is the so-called root of the tree. Now, we might insert 50, and the thing is anything less than 100 goes into what's called the left subtree, and anything greater than 100 goes into the right subtree. So if we now insert 25, it goes here. If we insert 75, it's less than 100 but greater than 50, it goes here. If we insert 80, it's less than 100, so we go here to 50. It's greater than 75, it goes here. So we keep the values organized in what's called a tree. Okay, this looks like an upside down tree. Okay, trees get all bushy and leafy. And as long as we keep this structure relatively balanced, it turns out that we can store n elements if it's balanced. It requires log n levels if it's balanced. And you can kind of see that because this is 1, 2, 4, 8. So at each point we're doubling. So if we store n elements, the bottom level, the top one can store 1, the next one can store 2, the next one can store 4. If you keep dividing n by 2, that's log n. So you can essentially do log n levels. You can see each comparison eliminates one level and moves to the next. So as long as the tree is balanced, we only need log n comparisons. So that's the general idea behind sets and maps, is we use what's called an underlying tree. And there are algorithms we can use that ensure that these trees will be pretty much balanced. Okay, but we will get to that. If you look at the notes, you will see at the end the basics of trees, binary search trees, AVL trees. These are all things we will get to in November, but we're not there yet. Okay, so sets and maps, they essentially have the same interface as hash tables. We want to do insert, find, and delete. Okay, so there is an insert operation. Now, the difference between a set and a map, a set only stores keys, and a map stores key value pairs. Okay, normally you want to store key value pairs. So sets typically aren't quite as useful as maps. But there are uses for sets. So for example, let's say that we have a list of voters and someone wants to register to vote. Well, before we register them, we want to see if they're already registered. Okay, that's a set. All we care about is this voter already in the set or not? In Lab 7, where you're processing Coke codes, you can enter codes, and all that matters is the code in the set or not? Is it a valid code or not? So sometimes all you care about is something in this set or is it not? And then you use the set data structure. More often, you care about having a key value pair, such as we have a set of candidates. For each candidate, we want to know how many votes they have. Hence, the key is the candidate name, and the value is the number of votes. Or the key might be, in the Coke lab, the username, and the value is an object which represents information about that user. Yes?
So like websites where you enter in like codes or whatever, do they have then basically just a giant list that you enter code searches for that?
Yes. So the question was, so if basically you have a website where you enter codes, is it essentially just keeping a huge list of codes? And the answer is yes. Now, it may be keeping it as either a set or a map. If the code is associated with prize information, it may actually keep it as a map. Or if it's just trying to determine if it's a valid code, it might keep it as a set. And of course, since you probably don't need to keep it in sorted order, codes are generally random, you'd actually probably keep it as a hash table. But Lab 7 is introducing us to maps and sets, so we use maps and sets in Lab 7, even though for the most part, you could use hash tables. Okay, so at any rate, and then there are multi-sets, which may store duplicate keys. So sets and maps don't allow duplicates. So multi-set and multi-map may store duplicate keys, whereas sets and maps, duplicates not allowed. Okay, so pretty simple. Here's just a program that is reading the lines of a file, inserting them into a set, and printing them out in sorted order. So we get here's the declaration. We're storing a set of strings. So insert inserts it. And then, just like lists, we have iterators that allow us to run through the collection and print out the value. So the syntax for iterating through a set or a map or a list is the same. You use iterators. Okay, so insert, pretty simple. Okay, then as you can see, here's a multi-set. So if you have duplicate names, you could use a multi-set to store them. So here he has several duplicate names that he's inserting, and of course they come out in sorted order still. Okay, the find method allows us to find items, and find returns a iterator. So find key returns an iterator. Okay, if the key is found, the iterator points to the key or points to the set element that stores the key. And if the key is not found, iterator points to .end, whatever is returned by the .end function. Essentially, it points to the Sentinel node. So points to the Sentinel element. Okay, so here he's simply entering a set of names and then searching for them. So after simply inserting names, he is asking the user to enter a name. And if the name is equal to names.end, he says it's not in the set. Otherwise, it is in the set. So find is pretty simple. And then delete is actually erase. Does he have it? Nope. Okay. So you can erase. Make sure about that. Do what I always do. Go to C++ reference. Set. And well, since I'm bored, come on. It's erase. And that's not working. Okay. So if you want to erase, if you want to delete, erase takes an iterator and deletes that element. And if I'm not mistaken, erase iter1, iter2 would delete all elements in the range from iter1 to iter2. And you'd have to check to see whether that's inclusive or not. There we go. So different forms of erase. And it actually looks like you can also call erase with a key. In which case it erases that key. Okay, so 3 versions of erase. Okay, maps, they're essentially the same. They also have insert, find, and erase. And erase essentially works the same way. Find and insert work a little differently. Okay, because insert, you have to insert a key value pair. And with find, you may want either the key or the value. So it's a little bit different in terms of syntax. And the way you handle that is that, first of all, in your map, you specify the type of the key and the type of the value, just like you did with hash tables. So this is saying the type of the key is a string, the type of the value is an int. Okay, and now if you want to insert something, you use this function called makePair, which creates essentially a struct. We'll call it a class since you haven't been introduced to structs. And essentially it's a class that has 2 public members where the key type is called first and the value type is second. So in this case, this map, it would be string would be the type of first, and int would be the type of second. Now, Dr. Planck says it would be so much nicer if these 2 fields were named key and value, but they didn't name them that. They named them first and second. At any rate, when you insert, you don't have to worry about that. You simply call makePair, pass it the key as the first argument, and the value as the second. Why they couldn't have made it easier and just given you an insert function that takes a key and a value beats me. But that was their decision, not mine. So, in fact, insert takes a single parameter. This is a single argument, which is a function that's returning an instance of that object. Okay, and when you are iterating through, you are getting pointers to those pairs, and hence when you access first and last, you need to use the arrow because you're getting pointers. So the iterator is a pointer to the pair, which is just like it is with all other iterators, except with list and set, the pointer is to a single element, so you use the dereferencing star operator to get to the element, whereas with a map or a multi-map, the iterator is pointing to an object, therefore you have to use the arrow to get to the 2 fields. Is that clear? Okay. Then we have a find. There we go. Here's a find. No, that's what it is. Okay, so here's a There we go. So here's a thing with maps where what we're going to do is count the number of NFL players that have, for each name, we're going to count how many occurrences of that name there is. So obviously with Van der Zanden, there'd probably be only one player, but maybe with Smith or Malone, we might have multiple players with that first name. So to do that, we keep a count. The value is going to be the number of players with that name. So we read players' first and last names. The find returns an iterator. Again, like with sets, if it's not found, it's a pointer to the sentinel node. So in that case, we make a pair with the last name and 1. Otherwise, we just increment second. Very simple. And at the end, very conveniently, we're printing out, since the map keeps the names in sorted order, we can print out the names in sorted order. So very simple. Okay, and one other reason that we use maps and sets often in C++ rather than hash tables, maps and sets are in the STL. Hash tables, I think, are a recent addition to the STL, but they're not always supported by all compilers. So that's why you often see maps and sets used even when hash tables would be more appropriate, because in their infinite wisdom, hash tables were not included in the STL originally. Okay, one quick thing, because this could bite you. You will be starting the Coke codes early next week lab, is that when you store elements in a map, the value field should be a pointer. If it's not a basic type like an int or a string. It's okay to store strings as values, but if you are storing objects as the value, store them as pointers. So if you store objects such as sets or classes or vectors as the value, store a pointer to that value. I will explain why on Tuesday. Basically, the reason is that if you store the value as an object and you retrieve that object through a find, you will get a copy of the value. And if you then modify that copy, you won't actually be modifying the value in the map, you'll be modifying the copy. And in your lab, you'll be baffled that you seem to be modifying the value in the map and it's not getting updated. And we'll get a Piazza post saying, I am updating values in my map, but they're not taking effect. And the reason probably is because you were storing the objects rather than pointers to the objects. And that's your difficulty. I'll go into more detail on Tuesday why that's the case.